Hello guys, welcome back to my channel. In today's video, we are going to train a neural network to detect the facial expression. By the end of this video, you will be able to do something like this. So first of all, I'll request you guys to go ahead and create a folder inside your Google Drive name as facial expression as I have created over here, because in this folder we will be keeping all our required datasets and artifacts like trained model and all. So first create this folder, and inside this folder just place this file over here, and I have shared a link in the description for downloading this file. So once you are done with all this thing, let's go back to your Google Colab, and we are going to write our code from scratch. So we are going to create a new notebook. Let's create a new notebook, and let's give some name to this notebook named as facial expression. So we are going to mount our Google Drive here. So let's import some of the basic libraries from google.colab import drive. Now let's mount our drive, drive.mount plus content. We are done. Let's mount this. And as like always, it is going to redirect you for the password to your Google Drive. Right now it's just connecting to the, and you have to authorize this. We have authorized the drive. Now let's go back and check where we are right now. So it is saying that we have reached over here. So actually we have to use the magic command to get into the folder. So we will use cd drive. We have just created this folder, facial expression. This is the good thing. This notebook also tells you the suggestions. Let's run this, and now let's check where we are. So as you can see, we have reached inside our folder, and now we have this zipped file over here. So this contains all our training dataset, testing dataset, everything inside it. So we need to extract it. So I got a pretty good script on Stack Overflow that I'll be just copying and pasting. You will get this script in the description. So here is our script. So basically it's a library named as tar file, and you can extract all your tar files by this library. So we are running this part, and once you will run this code, you will find that all your files will be unzipped. Let's go back to your drive, reload the page, and you can see this FER 2013 folder available within your drive. Let's open this, and you will get these three files over here. Actually, all your images are saved in the CSV format, and I will explain you how the images are saved. So we will go back to our file. We will import some of the basic libraries like TensorFlow and all. So we are going to import OS, import NumPy, import TensorFlow, I'm missing up pandas. For now, we'll import only these many libraries. We will see if we'll need some other libraries in future. On demand basis, we will keep on importing them. So here we are, and let's load our dataset as in pandas data frame. So I'm going to write df is equal to pd.read csv, and here we have our csv file saved inside this folder named as fer 2013, fer 2013, and our file name is fer 2013.csv, and let's print the head of this data frame. So here is our file. So if you see over here, we have emotion, we have pixels, and then we have uses for training and testing. I'm also opening this file in Excel so that we will have a clear idea that how this file is actually containing all the image datasets. So here is our Excel file. If you see over here, we have emotions, then we have pixel values, and this contains all the pixels of the image. There is a gap between each and every single pixel, and this complete line over here, it shows an image. Our image is actually created by multiple pixels, so these are the pixel values for individual pixel for that image. And in the first column we have emotions, and these emotions are labeled from 0 to 7, and I will tell you what each single label tells here. Now in the last we have uses. You can use that as in training or as in testing. Now let's go back to our notebook, and if we check the unique values within the emotions, we can do like df.emotions.unique. And here you can see that we have emotions starting from 0 to 6, and they are not arranged in ascending order, but you can see all the numbers starting from 0 to 6. So now we have a dictionary mapping for each individual emotions, and I will give this dictionary in the description so that you can directly follow it from there. And this dictionary tells that 0 is encoded for anger, 1 is for disgust, 2 is for fear, and 3 is for happiness, and 4 is for sadness, 5 for surprise, and 6 for natural. So I just got to know that the details of the author of this file. So complete credit for creating this file goes to the author, and I have added the complete details about the author of this file in the description. Now here we will use this label to text file to map our dataset to the actual labels in the last. For now, just save this as a variable. This file contains 48 cross 48 pixel size images. For decoding this file, I'm going to do df.pixel. Now we will take only the 0th one, and here you can see all the pixels. For converting this into a NumPy matrix, first we need to apply split. That is going to split it based on the spaces. If you see now, it has become a list. So we have to convert this to a NumPy array. And here is our NumPy array. Now we need to convert this NumPy array to 48 cross 48. So we will apply reshape 48, 48. Here is the image decoded after applying this reshape, and you can see this image by applying pyplot that we have imported from matplotlib dot imshow. So we'll use imshow method. Now we will just put this complete thing inside this. Oh, looks like we got an error, because if you see the element within the array, they are actually coming as a string. So we need to convert it to a float. So we will do as type over here, and we'll write float. Now let's see how the image looks like. Nice. So you can see the image is coming pretty correctly, and looks like our dataset is pretty good to go ahead. So guys, for looking up all the images at once, I have written down a code just for the visualization part. I'm just using it over here, and you will get this part of the code in the description. So here is that part of the code, and it generates a figure of 7 cross 7, and you can see it just for visualization of the image, so we can see multiple images at once. So if you go in the code, you will see that I'm doing the same thing what I did for the single line. Here I'm, instead of doing it once, I'm applying up a loop over here so that it can go one by one to each image and show the plot as well as the label for that. And you can see some of the images coming out pretty beautifully. Guys, let's parse out the complete data frame and create the training and testing data set. We'll apply some of the NumPy tricks to parse this complete data set. So let's write image array. And as you want to iterate to the data frame, we will apply a lambda function. So we will write df dot, we know that the column name is pixels. So I'll just copy it from here. Now we need to apply lambda function over here. So we'll write lambda, and we'll just copy this part from here because it just parse out a single line. So guys, this lambda function is actually be applied line by line to individual line of this complete data frame. Now let's run this. Okay, seems like we have to apply X over here. That's all. And guys, this is going to take up some time because it has to apply this function to individual line, and we have around 30 or 40,000 line in the data frame. So let's wait for some time and let this function get finished. Okay, it is done. So we can see the shape of this. So seems like it is not staked up. It has everything in single line. So we will apply a stake command over here. Now let's check the shape of this image array. Now you can see that you have 35,887 images, and each and individual image have shape 48 cross 48. If you want to see how this image looks like, we can just take the first element and we can write pyplot.show. And you can see the first image is coming up, and you can see the second part. So all that data frame is now parsed out to a NumPy matrix, and you can easily utilize this to train up our neural network. So eventually guys, you will also need the labels for individual image. So we will also take out the labels. You can write labels is equal to df dot emotions dot values, and this is going to give me all the values within this data frame, and this label will be an NumPy array. And you can see over here it is ND array with the same shape of the image. This is the time to split the dataset into training and testing parts. There is a good library within the sklearn for breaking up your dataset into training and testing parts. So we will use that. So I'm going to import that library from sklearn dot model selection import train test split. See if you get it. Okay, nice. And I will just keep this in the top because I do not want too many imports over there. So we'll just add it this to this line. Let's run this. Eventually this library is going to return you 4 items. First one is xtrain. So let's write this down. Xtrain, then ytrain, then xtest, ytest. Let's make this x capital. So we'll use this here. Takes your image array. Now it takes your labels. So we need to give test split is equal to 20%. Let's take it 20%. Now that's all guys. Just run this and see if you are getting, sorry, it is test size. So here we are. So we want to check how the output looks like from this train test split. So I'm going to just do xtrain.shape, ytrain.shape, and xtest.shape and ytest.shape. Oh, looks like we have taken it wrong. This is xtest and this is your y train and the other one is ytest. So guys, it's very necessary to check out if the variables are coming correctly or not. You can do it by checking out the shape. Now you can see the test shape is coming out clearly correct, and we have y train shape is also pretty good. And also let's take this test site little smaller. A good practice to divide your training images by 255 because it will pull out your images from a range 0 to 255 to a range 0 to 1. So we will do the same. We will write xtrain divided by 255 and xtest divided by 255. Now this is the time to create or declare a TensorFlow model. We can do it with base model is equal to tf dot models dot sequential. Now within this bracket we are going to define all our layers, input shape, output shape, everything. So let's add up our first layer over here, df.keras dot layers. So we will add con 2D over here, and within this con 2D you need to provide these all things like filters, kernel size, strides, everything. So let's give number of filters. We wanted to have 32 filters. We are going to take a 3 cross 3 con filter, 3 comma 3. Now you have strides. I do not want to give any stride. We have padding, data format, dilation rate, group, activation. So we will give activation over here. We will give value over here. Now let's put up a comma. Then as it is the input layer, so we'll give an input shape also. Here the input shape will be 48 comma 48 comma 1. So guys, this is really important to define the input shape because it is the first layer. In other case, you can define another layer as an input layer, then add this con layer after that. But I do not want to write two lines, so that's why I have just defined this complete thing in one line. So you can see that we didn't get any error. And just for checking out your model has created correctly, we'll see base model dot summary. It's always good to check out the summary of your model. So you can see that everything is coming pretty correctly. Now we can add up more layers to this con layer. So we'll just go one bracket over here. We know that whenever we are defining a convolutional neural network, we always go with a max pooling layer next to our con layer. So I'm going to apply dot keras dot layers. We will add the max pool 2D and we'll apply this max pool 2 comma 2. That's all. Now let's check if it is coming up correctly. We are again going to run the summary. Your max pool layer is added correctly over here. So we can either add up a bash norm layer next to this one because we wanted our data to be normalized after every iteration. So I'm going to just add a bash norm. Keras.layer and add up a bracket. You do not have to give any details for the bash norm layer. Now let's check if it is coming up correctly. The summary is coming up correctly. Our bash norm layer is added. Now you can add up additional layers, but what I'm going to do over here, I'm just going to copy paste some of these layers next to it because we want to add these layers multiple times. And don't forget to put up the comma. Now here we can just put up a slash just to say that we are going from one layer to next layer. And guys, I've seen that it's a good practice to increase the number of filters while going deeper. So we're going to change it to double of the first one, 64. Then we are going to have 128 over here. And that's all. Our model is now defined. Let's check our summary. And here you can see all our layers are added. Now we can add up a dense layer next to this. Keras.layers. And this dense layer should have the shape what we are coming at the last. We are getting 128. Let's put up 128 over here to keep our activation value. And at the final, we need to add up a dense layer with softmax because it's a multi-class sort of classification. So we'll add up one layer over here. And this dense one will have only 7 because we are going to get 7 classes. And the activation will be softmax. That's all. Now let's run this. Put up an S over here. Let's run this. Good. Now let's check up the summary and see if our model is working up correctly or not. So guys, you can see over here we are getting this 4 cross 4 at the final, which is not a good thing. To add up a layer over there, so we first have to flatten our output once we are coming out from this max pool. So we will just do df.layers, df.keras.layers.flatten. Let's see the summary. And here you can see our complete sequential model. Whenever you are training up your model for more number of classes, like I have only 7 classes over here, that's why the output layer shape is 7. If you are having like 10 classes, make sure you are changing up this number over here because this is going to define the final class or the number of class for your output layer. And based on this only, your model will start training. It is the time to compile our model. So we will do base model dot compile, and here we need to provide the optimizer. As you can see, it's also giving us suggestion. So we are going to use RMS prop because I have seen it's working pretty well. df.keras.optimizer, and here we are going to use RMS prop, and inside this we have to give learning rate. And guys, if you check this dataset, is not that great. There are a couple of images which have not labeled correctly, but most of the images are labeled correctly. So we are thinking to get a good amount of accuracy. In my previous video, I have seen that many of you guys were having issues on here itself. Like whenever you are trying to train up your model, you are getting an error that your shapes are not matching. So this is mostly because of the loss over here. So whenever you are giving the loss, and if you are defining it as a sparse categorical cross entropy, it means all your input vectors over here, the labeled one, if you see this shape, 3298 images are actually not one hot encoded. So if you are providing this sparse categorical cross entropy, it is going to first one hot encode your vector, then start the training. In case you are already having the one hot encoded vector, you have to take categorical cross entropy over here. Okay, make sure that if the vector is one hot encoded, this train vector, you are taking up categorical cross entropy. And if it is like this, what we are doing right now, you should give sparse categorical cross entropy. Otherwise, you will face errors while your training starts. And we want to iterate for good accuracy. That's all. Let's run this. And your model is now compiled. You can actually start training after this, but I want to have a callback function which checks out your validation accuracy in each iteration. And at the time you stop improving on the validation dataset, you won't save your model. I'm going to create an create a folder with the os command. For that we need to import os, and then we will use os.mkdir. So here we will be saving our model. So I'm going to create a checkpoint folder. Okay. Sometime if you have already created this folder, it will throw up errors. So we will just write try and accept. We'll just type pass. So this is going to create a checkpoint folder within the folder where you are currently. So if you go back to your G drive and you will find this folder as in checkpoint over here. Within this checkpoint folder, you will find your models to be saved after the training. So we'll just define a variable named as file name, and this file name will contain the best model. Now we will just write checkpoint path, and we just have to write os dot path dot join, and we want to join this file name with the checkpoint so that it will get the path to that file. So we'll just write checkpoint. This is the folder we just created. So we are just adding up the path of that folder where we want to save the file and the name of the file. So here we need to just write h5 file. So that's all. We have defined our checkpoint, and I have a short code that saves us the file. So I'm just going to copy and paste that code over here. You will get that code in the description, and I will explain you what that code is doing. So this is the callback code. So it takes up the callback model checkpoint, and here it takes up the path of the file. You want to monitor the validation accuracy, and you want this verbose is actually saying how much print you want to see on the screen. Then you want to save frequency is each individual epoch. The best only is equal to true. It means you do not want to save all the models. Save weights only is equal to false. So you want to completely save your model, and you want since you want to maximize your validation accuracy, so you have to write max over here. You can also do a loss validation sort of loss, then you can have to write minimum over here. Let's run this. Okay, I did some typo, and that is over here. Good. So now let's start the model training. So we'll write base model dot fit, and here we actually want to use our training dataset x train and y train, and you want to iterate for 10 epochs or 20 epochs, and we want to check the validation split as in 0.1. So we'll be keeping 0.1 for our validation split from this training dataset, and we want to have the callback. We want to have the callback is equal to callbacks that we defined right now. If we start training up our model, actually our X-train shape is, if you see the shape of your X-train, you'll find that this is 32,298 and 48 and 48. But if you see our model, we have given 48, 48, 1, which is actually a incompatible sort of version because you have to provide channels also. So what we will do when we'll go back over here, and where we were reshaping it, we will add up an additional dimension to this one as in 1. Now we will run this, and this is going to again take up some time. Run this, run this, and you can see that that additional dimension is now added to your X train and your X test. Now again we have to run this one, and here you can see our training has started, and it is achieving the better accuracy. We will wait for some time till the time it trains up, and this is going to take up some time because we have a huge number of images in the training dataset. And additionally, when you are trying to train up the model, you can go to the runtime and change the runtime to, you can change the runtime type to GPU and get the faster acceleration for model training. So guys, I was little impatient, so I changed the runtime to GPU, and here you can see how fast it is running now. So you can also try out the GPU one because it's pretty fast, and you can see we got a good accuracy till 5.1, but it's not that much improving. So guys, seems like our validation split was very small, and all the classes which were not getting predicted correctly were there in that small split. So I just increased some size of the validation split, and also also added one extra layers. You will get this complete code of this base model in the description of this video. So you can just copy it from there. Then with this configuration, you can see we are achieving a good shot of accuracy around 78%. And it is quite good because if you see the training dataset that we are going to see now is not that great. So I'm going to stop it over here because we have already got a good model based on the dataset, because this dataset is not that great. Let's stop this model now, and we have this best model already saved over here, this one. So we'll just load this model and we'll start predicting based on this. So this part of code I have written so that it just takes out the model and predict the class. Now we are just taking the 40 first images. Then we are printing the actual labels based on the test y test. And then we are predicting up the class from this line. Here we are just applying this predict function, and make sure you are expanding the dimension because it requires sometimes it throws up error when we want to apply the same dimension of the model training. Then we are taking the argmax. It means 7 classes. It will say like fifth class is the prediction. We are taking the fifth prediction from this list, and then we are just printing out our image and then just stopping for some time, and then we are clearing the output from this Jupyter notebook so that we can, when we go to the next iteration, we can show up new output over here. So before we get into this code, we first need to load up our model. So I'm just going to write final model is equal to df.keras dot models dot load model, and here we just have to provide the address of our file, that is checkpoint and file size. So we'll just put this checkpoint path, and if you see what is there inside this checkpoint path, you will get to know that it's a path of that best file. So we'll just do this. Now it is going to load up the model and it is going to predict for each image. Oh, if you see over here, it is saying now it's not correct for the image size because we used this for training up our model, but you know that matplotlib doesn't take three shape tensor as an input, so we have to reduce this tensor to 2. So we just need the 48 cross 48 part, not this one. So we'll just go over here where we are doing this, and we are going to do reshape, and we are going to reshape it to 48 comma 48. Now eventually, if you can see this is saying it is fair, this is natural. If you see over here, these images are quite so it is saying this one is fair, which is actually correct. Let me just reduce the speed so that we can focus on individual image. Let's make it 5. Now run this, and here you can see the predicted label is fair and the actual label is also fair, and the actual label is actually fair, but our model is saying it is natural. And here we are correct, both are saying fair. Then you can see happiness is coming pretty correctly. Here the fair is also coming correctly. So that's all guys. If you have liked the video, don't forget to press the subscribe button and the bell icon. because we used to come up with such videos every single week. I will catch up with you in my next video. Till then, bye bye and take care.